Yeah, thank you, Arben. So, good morning and good evening, everybody. So, yes, I will summarize the work that has been done over the last years to better understand and also to quantify the spatial variability of the near surface properties in the Grenoble Basin. So, I will present the work. However, this is really a collaborative work with a lot of people from geology and geophysics that help a lot to improve the model. So I will start first with the Grenoble model, the model that was used during the ESG 2006 benchmark. So during this benchmark, the goal was not so much to compare simulation with observation, it was more to compare different simulation schemes. So in order to build the Grenoble models that was used during this benchmark, we were using the surface topography, we were using the bedrock topography coming from gravimetry measurements. So you have in the middle the bedrock topography, and you can see that in the center of the basin, the sediment thickness can reach 1 kilometer. And at a deep borehole site, we also measured VP and VS profiles done to the seismic bedrock. And we could also infer the attenuation values, so QP and QS. So basically, the model used in 2006 was using these three main ingredients. So after the benchmark, we ask ourselves, okay, we did produce a model. Is this model able to reproduce observations? So it's very difficult in Grenoble to compare simulation with earthquake recordings because Grenoble is not a very high seismicity area. So the first step was to use the 3D model and to simulate seismic ambient noise. So this is what I have done between 1.2 and 1.1 Hertz using the finite difference scheme proposed by Peter Moxo and Joseph Krzyzek. So I did simulate seismic ambient noise at different sites in Grenoble and do the comparison with the actual ambient noise recordings. And when we look at the comparison between the H over V peak frequency for real noise recordings and noise synthetics, we can see that the distribution of resonance frequency are very good or very similar. And with the simulation, the noise synthetics, we could reproduce the H over V peak frequencies within 20%. However, we could observe some large differences close to the border here due to the fact that the velocity structure of the close to the border is not so well known. And also in the basin center at some sites, we could observe that with the synthetics, we slightly overestimate the actual H over V peak frequencies. Another comparison was done by using ambient noise simulated or recorded at array sites. So here we have at that time 4 array sites. And here this is the dispersion curve for the Rayleigh wave fundamental mode as a function of frequency at the borehole sites and at the site Bonpasteur. What we can see is that the data are in red and synthetics in black. And we can see that the ESG 2006 model is quite nicely reproduce the observation in terms of phase velocities. However, we can observe from arrays to arrays that above 0.8 Hertz, usually we observe either a slight under or overestimation of the phase velocity. Anyhow, overall, this model that was proposed 15 years ago, we think this is very suitable to reproduce H over V and dispersion estimates up to 1 Hertz. Now, if we look at the couple of earthquakes that we recorded in Grenoble, and if we simulate the earthquake, so this was done by Emmanuel Chaljup for a small magnitude earthquake that occurred in the south of Grenoble, magnitude 2.8. Here you have at the borehole site the synthetics and the recordings. So what is represented here, these are velocities that are bandpass filtered between 0.5 and 1.5 Hertz. So we can reproduce the amplitude of the first arrival, but definitely with the simulation, we fail to reproduce the long duration of the ground motion. And it means that the velocity model in terms of the velocity and attenuation structure in the sediments and rock has definitely to be improved in order to be able to reproduce these late arrivals. So one of the first things that we did after observing this inconsistency between synthetics and recordings was to look at the near surface geology in Grenoble, because we know that the infilling history of the basin is quite complicated. In fact, the sediments are coming from two glacial, interglacial cycles. And after the glacial cycle, we have an erosive phase. And during this erosive phase, the basin was filled by a lake. And the lake, then we have the deposits from the lakes, which are fine homogeneous sediments made basically of sandy and clayey silts. And then these lake deposits were covered by heterogeneous alluviums coming from two rivers, the Drac River and the Isère River. So the Isère River that is shown here in blue, this is a very calm and quiet river, and the alluviums are made of fine deposits like clay and silt, while the Drac River is very energetic. We know that we had several large floods in the past, and this river leads to deposits, to very coarse material deposits such as gravels and sand. And the Drac River, interestingly, in the 13th century, the Drac River was, the bed of the Drac River was covering all the city. And then from century to century, inhabitants tried to focus the bed of the Drac River until the actual position of the Drac River, which is here. So we know that in the sediment, in the basin of Grenoble, we have alternance of clays and gravels coming from the floods of the Drac River. So in order to have a better idea about this geological heterogeneity in the near surface, what we did collect more than 1,300 geological or geotechnical logs. So we were using the National Borehole Database, and we were also collecting by ourselves geological logs. So the type of information we had, we had Andina penetrometer test, destructive drilling description log, like this one, and pressurometer test, and also resistivity diagraphy. So our geologists spent quite some time to analyze this data, because this data, we have it on paper, we have no digital information. And here, this is a map showing the location of the boreholes that were collected over the last years. So the first geological analysis of the geological logs shows that in the near surface, in the first 20 meters, we have mainly gravel or sand or clay. And we can see also that we have a large lateral variation of the surface geology at the basin scale, but also at local scale. So at the basin scale, here, this is a 4 kilometers length cross-section here. And you see that on the western part of the basin here, we have mainly gravels that are overlaying the lacustrine deposits coming from glaciers. And on the western part, we have clay that overlay gravels and then the lacustrine deposit. And there are also some parts in the city where we have gravels unit inside the clay formation, and these gravels are coming from the drag fluid. At a more local scale, this is another cross-section here, and this is a 1 kilometer length cross-section, and the color represents different geological facies. And we see that we have a large spatial variation of the near-surface geology. Also, during the past years, we acquired and collect a lot of geophysical measurements. So basically, we have 110 sites with active surface wave measurements and 15 sites with passive surface wave array measurements that are indicated here in the two plots. And when we look at the relay phase velocity for the fundamental mode, here in gray in the figure, you have the phase velocities extracted from array measurements, and in black, the dispersion curve coming from active surface wave measurements. What you see is that below 1 Hertz, we have phase velocities that are very compatible with the ESG 2006 theoretical model. Here in red, this is the dispersion curve for the ESG 6 model for a bedrock depth of 850 meters. And here in blue, this is for bedrock occurring at 200 meters depth. Between 1 and 5 Hertz, it seems that the phase velocities that we observe are lower than the theoretical phase velocity, which might indicate that we have that the VS profile in intermediate to deep layers is slightly lower than the one prescribed in the ESG 2006 model. And at high frequency, we can observe that we have a very large variability of the near surface geology. And when we try to look at the depth range related to this large variability, we realize that we have a large variability of the near surface velocity within the first 20 to 30 meters. So then we have in Grenoble a lot of geophysical measurements. However, these geophysical measurements are not enough in order to enable extraction or quantification of the spatial variability of the VS profile in the first 20 meters. So what we did, we tried to make the best use of the borehole sites. And we did some specific MSW measurements at borehole locations in two zones where, in two specific zones, in order to try to correlate the geological facies with the shear wave velocity. So we did some surface wave measurements, and we did constrain the surface wave inversion with the geological information, which lead us to nicely correlate the geological facies with the shear wave velocity structure. And here we have, for the main facies in Grenoble, so backfills, gravels, pit, clay, and sand, the measured mean VS together with the uncertainty. So then at each borehole sites, we use the borehole sites in order to derive a velocity structure at the borehole sites. And in the following, I will show you I'm showing the VS10 values in Grenoble coming from these borehole sites. And you see clearly that in the center part of the valley here, we have VS10 values that can be large, up to 400 meters per second, while on the western part, you can have VS10 values as low as 100 meters per second. When you zoom in this zone here, So we have here a clay-dominated formation, here a gravel-dominated formation, and we see that the lateral variation between clay and gravels is very abrupt, and the related velocity is also very abrupt. And this is coming here. We can clearly see that this lateral variation is fully controlled by the activity of the Drac River.
5 minutes.
Yeah.
You are 5 minutes.
Okay. For these sites here, what we could observe is that we have some small scale variability of the VS10 values that are in relation with some extreme flooding of the Drac River in the past. This river with gravel materials. So next, we try to compare the phase velocities distribution for VS profiles derived from surface wave measurements and from borehole data, because for the borehole data, we did the correlation between VS and geological facies only at 2 specific sites. And we can see that we have very consistent phase velocity distribution between geological information and surface wave data. The next step was to try to say, okay, now we need to quantify the spatially variable elastic properties. And here I will show you the main principle. So here you have different layers. And within a layer, you have the soil property. And the soil property can be described as a trend plus an autocorrelation function that describes the fluctuation of the soil properties around the trend. And when we measure autocorrelation function, we can then have an estimate of the fluctuation scale of the soil property and the autocorrelation distance. So this is what we are trying to do in Grenoble, to measure the mean VS, the coefficient of variation, and the autocorrelation distances in the horizontal and vertical directions. So just before showing the results in Grenoble, I just wanted to show these slides provided by Dalia Youssef Abdelmassi 2 years ago. And they try with Nancy Saloum to, they look in the literature and they were looking at papers that were dealing with the quantification of the uncertainty in rigidity of the near surface material. And there are only a couple of papers addressing this issue. And from the paper, we can see that authors, they do report a coefficient of variation related to the rigidity that is close to, in average, close to 25–30%. For the vertical autocorrelation distance, we see from literature that it's ranging from 0.5 to 2 meters. And for the horizontal autocorrelation distance, which is difficult to measure, we have values ranging from a couple of meters to 400 meters. However, when we look deeper in the papers, we see that sometimes the spatial sampling is not always respected when people infer this horizontal autocorrelation distance. So now I will go directly to the quantification of the spatially variable elastic properties in Grenoble. So what we did only select those boreholes that goes to 20 meters depth, and we did measure the coefficient of variation of VS and the horizontal autocorrelation distance using an exponential decaying autocorrelation function. And what we can see in this zone here that will be served for numerical simulation, that in the clay formation, we have a coefficient of variation which is close to 30%, while in the gravel formation, we have a coefficient of variation close to 40%. If we now look at the horizontal autocorrelation distance, even though we have a distance that is slightly slower in the clay formation compared to the gravel one, in average, we have a mean autocorrelation distance in the horizontal direction that is about 20 meters, which means that the fluctuous scale, which means that we have a very large spatial variability of the VS structure in the near surface. So this value of coefficient of variation and autocorrelation distance, we found similar range of values in the B and also in the C areas. So as concluding remarks regarding the Grenoble's model, I would say that the ESG 2006 model is definitely too fast in the first 20 to 30 meters, that we have a very large variability of VS in the first top 20 meters that are in relation with the history of the infilling of the Grenoble basin and in relation with two rivers. And regarding the spatial variability or the quantification of the spatial variability of the elastic properties, we have coefficient of variation that are of the order of 30 to 40%, and an horizontal autocorrelation distance that is close to 20 meters, which means that I think to model or to simulate ground motion in the high frequency range for Grenoble, this is definitely a numerical challenge. Voilà, thank you for your attention.